Welcome to AI Paper Slop. Today, we are doing a deep dive into a paper titled Robots Acquire Manipulation Skills in Seconds from a Single Human Video.
Such a wild title.
Right. And look, if you're an ML engineer or an AI researcher trying to get physical systems to actually do things in the real world, you know how painful the deployment pipeline can be. So let's just get right into the core insights.
Yeah, let's do it.
So researchers from the Beijing Institute of Technology, X Square Robot, and Tsinghua University have developed this framework called HOST. That's Human to Robot One-Shot Skill Acquisition.
Love a good acronym.
Oh, always. So here is the bottom line up front. HOST enables a robot to learn novel manipulation tasks from literally a single human demonstration video. And it does this in an average of 29 seconds during inference.
Which is just crazy fast.
It's unreal. It achieves a 62% success rate, it requires absolutely zero task-specific fine-tuning, and it completely avoids the whole catastrophic forgetting issue of previously mastered skills.
That's the holy grail right there.
Yeah, seriously. And it works via this thing they call a cascade of self-grounded prediction. Essentially, it maps the human video to a shared task progress manifold, translates that into the robot's own future visual observations, and derives its actions directly from those predictions.
It's a completely different paradigm for training physical systems, honestly. I mean, to really appreciate why a 29-second inference time acquisition is such a massive breakthrough, you kind of have to look at why traditional skill acquisition is such a huge bottleneck.
Right, like why it's been the ultimate headache for ML pipelines.
Exactly. I mean, for a long time, the whole industry was chasing reinforcement learning. But if you're trying to deploy RL on a physical robot, you just immediately hit the reality of reward engineering.
Oh, yeah, because defining a dense reward function for something as complex as, I don't know, tying a shoelace or washing a dish is just an absolute nightmare.
It really is.
Like, in a simulation, you can just track the coordinates of the digital disk and the digital sponge and write this neat little math function. But in the physical world, how do you mathematically quantify cleanliness to a robot in real time?
We can't. Not easily, anyway.
Go ahead.
Plus, RL relies on trial and error, right? In a physics engine, you can run 10,000 episodes in an hour just by speeding up the simulation.
Yeah, just crank the clock speed.
Right. But in the real world, a robot operates in real time. If it drops a plate during trial and error, a human has to literally walk over, sweep up the glass, place a new plate on the table, reset the joints.
It's so painfully slow.
It's terribly sample inefficient.
Yeah.
And it's completely unscalable for complex manipulation.
Which is exactly why the field pivoted so hard toward imitation learning over the last few years, right? The logic was, well, why try to design an impossible reward function when we can just show the robot what to do?
Yeah, just give it demonstrations.
Exactly. So the standard pipeline now is taking a skilled human operator, strapping them into a VR rig, or giving them a specialized teleoperation joystick, and basically having them physically puppet the robot through the task to collect the data.
And, you know, to be fair, imitation learning has pushed the baseline forward significantly.
Oh, for sure.
By training on massive, diverse data sets of these teleoperated demos, we've achieved a level of generalization that was totally unthinkable a decade ago.
Yeah.
But acquiring a novel, completely unseen skill, it still relies on this painfully burdensome training time loop.
Yeah, it's like, okay, imagine teaching a sous chef a new recipe, but to do it, you have to physically stand behind them, grab their wrists, and puppet their hands through chopping a carrot 50 times in a row.
That is exactly what it feels like.
Right. It consumes scarce robot uptime, requires highly skilled human labor just to get the data, and then you still have to push that data to a cluster and run compute-intensive offline fine-tuning for hours just to update the network policy.
It's a great analogy, but the sous chef problem actually gets worse.
Wait, worse how?
Because once you spend those hours fine-tuning the model on the new carrot chopping data, you run straight into the brick wall of catastrophic forgetting.
Ah, right. This is the part that drives engineers absolutely crazy.
Oh, it's infuriating.
You update those shared network parameters to learn the new task. The gradients from the new data shift the weights inside the neural network, but in doing so, they just overwrite the delicate representations that encoded all the old skills.
Yep, they just wipe them out.
So as a reward for teaching your robot sous chef how to chop a carrot, it suddenly completely forgets how to boil water, which it already knew how to do perfectly yesterday.
Because fine-tuning inherently overwrites parameters that are shared across tasks. The loss landscape is optimized purely for the new data, which obliterates the previous equilibrium.
It's just so frustrating.
So the entire process is costly, slow, and ultimately kind of self-defeating if your goal is to build a generalist robot that just accumulates a massive infinite repertoire of skills over time.
Okay, so this sets up the fundamental problem perfectly. Retraining the network weights inherently causes catastrophic forgetting.
Right.
So the logical next step, and what this host paper attempts to solve, is figuring out how to acquire skills without changing those underlying parameters at all. Like, how do we do this entirely at inference time?
Yes. And that brings us to the host framework and this fascinating concept of a cascade of self-grounded prediction.
Yeah, let's unpack that.
So bypassing the training loop entirely is where host shifts the paradigm. The system breaks the problem into 3 distinct steps that run dynamically as the robot executes the task.
Okay, what are the steps?
Step 1, it constantly estimates the robot's current progress within the demonstrated human task. Step 2, it translates the upcoming progression of that human task into the robot's own future visual observations.
Okay.
And step 3, it derives the low-level physical actions directly from those predicted future visual states.
Wait, let me make sure I'm wrapping my head around this. Usually you try to map the human's joint angles, like the bend of the elbow or the rotation of the wrist, directly to the robot's joint angles.
Right, that's the traditional kinematic mapping approach.
But this isn't doing that. It sounds almost like the robot is hallucinating a picture of what its own mechanical grippers should look like, completing the next step. And then it just moves its motors to make that hallucination a reality.
Actually, hallucinating is a really accurate way to conceptualize it. Under the hood, the architecture uses an autoregressive diffusion model to generate these future states.
Oh, wow.
Yeah, what host does is transform the incredibly messy physics problem of learning a motor skill into a much more tractable vision prediction problem.
That is a massive distinction, because mapping biology to mechanics is just so inherently flawed.
Yeah, it's called the embodiment gap. I mean, think about it. A human hand has 27 degrees of freedom, soft tissue, tactile skin.
And a robot gripper might literally just have 2 rigid parallel fingers and maybe 6 degrees of freedom in the arm.
Exactly. So forcing a neural network to directly translate a human's biological state to a robot's mechanical action policy is incredibly difficult because the physical constraints are just entirely different.
Right. So by abandoning the joint mapping entirely and generating a visual target instead, the system sidesteps the physics problem entirely.
It really does.
It just predicts what the robot's physical workspace should look like in the immediate future. If the human video shows a hand grabbing a cup, the diffusion model hallucinates an image of the robot's specific gripper wrapping around that same cup.
And once you have that predicted visual target, the policy simply acts as a low-level controller. It actuates the joints to match the physical reality to that visual prediction.
That's brilliant.
It's actively adapting the human's abstract procedure to the robot's specific physical embodiment, all in real time.
Okay, but for this visual hallucination to be accurate, there's a huge prerequisite here. The model first has to perfectly map the human's movements and the robot's movements onto the exact same timeline.
Oh, absolutely. That's the hardest part.
Right, because if the robot doesn't know where it currently is relative to the human's demonstration, it has no idea what visual state to predict next. I really want to dig into the math of the alignment module here because it feels like the engine driving this whole capability.
Yeah, the alignment module is incredibly elegant, and it relies heavily on the capabilities of modern vision language models. The researchers use Qwen3VL embedding 8B as a shared encoder for both the human video and the robot's camera feed.
Okay, wait. Using an 8 billion parameter vision model to process continuous video streams sounds like an absolute memory nightmare.
Oh, it is.
Anyone who has tried to process long sequences of high-resolution video frames knows exactly how fast you hit an out-of-memory error on your GPUs.
Yeah, it is a massive VRAM constraint. So to make it work, they load the model in bfloat 16 precision and utilize scale dot product attention along with gradient checkpointing.
Okay, so a lot of memory optimization tricks.
A ton of them.
Yeah.
But the real trick is in how they extract the features. They don't just dump all the raw, high-dimensional image features into the alignment module. They extract the representation specifically from the end of sequence, or EOS, token position in the last hidden layer.
Oh, interesting. Why the EOS token specifically?
Well, in transformer-based vision language architectures, the attention mechanism forces the EOS token to act as a sort of aggregator.
Yeah.
By the time the forward pass reaches that final token, it has attended to, and compressed the global semantic context of the entire sequence up to that point.
Oh, so it's like a summary token.
Exactly. It's
Yeah.
essentially a highly dense semantic fingerprint of what is happening in that specific frame. Extracting from that position gives them a 1,536-dimensional hidden state per frame.
Still pretty big.
It is. So they then apply a learnable linear layer to project that massive state down to a much more manageable 128-dimensional embedding. And that's followed by L2 normalization to keep the scale consistent.
Okay, so let's visualize this for a second. You now have two sequences of these 128-dimensional fingerprints, right?
Right.
One sequence represents the semantic beats of the human demonstration video. Maybe it's an array of 100 frames. The other sequence represents the life trajectory of the robot, but you still have a massive temporal mismatch here.
It's a huge one.
Because a human is fluid. They might grab a towel and wipe a plate in 3 seconds, but the robot is bound by completely different motor velocity limits and might take 7 seconds to complete the exact same subtask.
Exactly.
So if you just try to do standard frame-to-frame matching, like aligning frame 10 of the human to frame 10 of the robot, the whole thing completely breaks down.
It falls apart instantly. Standard frame matching assumes perfect temporal synchrony, which, as you said, never happens across different embodiments.
Yeah.
You need to map both of these sequences onto what the paper calls a shared task progress manifold.
Right, and how do they actually build that manifold?
Well, to do this, they compute a pairwise similarity matrix. Think of it as a giant grid. They calculate the negative squared L2 distances between every single human frame embedding and every single robot frame embedding.
Okay, so this grid, this cost matrix, represents the mathematical cost of matching any random human frame to any random robot frame.
Yes,
A
exactly.
low cost means the semantic fingerprints look very similar, like maybe both the human and the robot have their hands hovering just above the plate.
Right. They're at the same semantic step.
But how do you find the right path through that grid? A path that makes logical, chronological sense from the start of the task to the end.
This is where they introduce smooth dynamic time warping, or smooth DTW. Now, dynamic time warping is a classic algorithm in signal processing for measuring similarity between two temporal sequences that vary in speed.
Right, it's been around forever.
Yeah, it finds the optimal path through that cost matrix. But standard DTW uses a hard minimum operator when calculating that path.
And a hard minimum is a death sentence for a neural network during training, isn't it?
It absolutely is.
Because a hard minimum is not differentiable. You hit a hard edge, the gradients can't flow backward, and you can't actually update the weights of that linear projection layer we talked about earlier.
That is the core issue.
Yeah.
If you use standard DTW, the networks simply can't learn. So they replace the hard minimum with a differentiable smooth minimum operator.
Oh, that makes sense.
Yeah, to use a physical metaphor, standard alignment is like trying to snap rigid Lego blocks together. If the human's timing and the robot's timing don't fit perfectly frame by frame, the connection just breaks.
Right.
Smooth DTW is more like using rubber bands to connect the steps. It dynamically stretches and compresses time, allowing the human's fast movements to map smoothly to the robot's slow ones without breaking the underlying connection.
Okay, that rubber band analogy makes so much sense. It's like a universal translator, but instead of translating languages, it translates time and motion.
Yes, that's a great way to put it.
It aligns the wiping the plate beat perfectly with the robot's timeline, regardless of how fast or slow either agent is moving. And because they use that rubber band-like smooth minimum, they can run forward-backward dynamic programming and recover soft matching probabilities.
And those probabilities enforce something critical here: monotonicity.
Meaning it only goes in one direction.
Exactly. The alignment path only moves forward in time. It preserves causality. You can never match a future state of the robot to a past state of the human demonstration. The loss gradients flow properly through the smooth minimum, training the network to perfectly align the abstract semantic concept of wiping the plate, entirely independently of the physical embodiment or the speed of execution.
So once you have this shared task progress, manifold, this perfect elastic temporal alignment, the rest of the cascade just falls into place. The model knows exactly where the robot is in the task. It looks at the aligned future frames of the human video, and the diffusion model hallucinates those future visual observations for the low-level controller to actuate.
Yep, the pipeline just clicks together.
It's a brilliant pipeline. But look, theory is one thing. As an ML engineer, I always want to know if this math actually survives contact with the physical world.
Oh, of course. The benchmarks are what matter.
Let's look at those benchmarks because, honestly, beating a baseline that was explicitly fine-tuned on 50 perfect robot demonstrations using just a single human video in 29 seconds sounds like science
It
fiction.
really does. But the quantitative results really push the boundaries of what we thought was possible at inference time. Let's start with the speed constraint. The skill acquisition takes just 29 seconds on average.
Unbelievable.
If you compare that to the conventional method of setting up a teleoperation rig, collecting data, and running offline fine-tuning, Host is 507 times faster.
507 times faster. That isn't just an incremental improvement. That is the difference between an academic research project that lives in a lab and a commercially viable system that you can actually deploy to a factory floor or a hospital.
Completely changes the economics of it.
And it achieves that speed while requiring 50 times less data. I mean, we are talking about one human video captured on a standard RGB camera versus 50 teleoperated, highly engineered state action paired demonstrations.
And despite using a fraction of the data and a fraction of the time, Host achieves a 62% average success rate across completely novel testing tasks.
Which is huge.
Yeah, to put that in context, it exceeds the standard zero-shot baseline by 45%. But the truly staggering part is that it actually beats the baseline model that was explicitly fine-tuned on those 50 robot demonstrations.
That is wild. It outperforms a model that was literally overfitted to the exact task using massive amounts of perfect robot data.
Yeah.
I mean, that speaks volumes about the quality of the semantic representations being extracted by that Qwen3VL encoder and just how robust that smooth DTW rubber band alignment really is.
It proves that the latent spaces inside these massive vision language models already contain a deep, intuitive understanding of physics and task progression. They just needed the right alignment.
Right.
But perhaps the most important metric for anyone listening who is actually trying to build a generalist robot is the retention rate. Because Host operates entirely at inference time, meaning it never once updates its base network weights to learn the new skill, it has 100% skill retention.
It literally cannot suffer from catastrophic forgetting because it never changes its foundational memory.
Exactly. Compared to those fine-tuning baselines, which suffer from the exact weight-shifting degradation we discussed earlier, Host shows a 56% improvement in retaining previously mastered skills.
Wow.
You could theoretically teach this robot 100 new tasks in a single afternoon using nothing but iPhone videos, and it will still execute the very first task from its pre-training data flawlessly.
That is incredible. And to really ground this, there are some amazing visual examples detailed in the physical experiments section of the paper that highlight just how complex these novel tasks are.
Oh yeah, the tasks are not simple at all.
Right, we aren't just talking about pushing a plastic block across a flat table here. One of the tasks involves a dual-arm robot washing a plate with a towel.
And dual arm manipulation is notoriously difficult in robotics. When you add a second arm, the action space isn't just doubled. The complexity grows exponentially because you have to constantly calculate collision avoidance between the two limbs.
Yeah, they can't just smash into each other.
Right. The coordination required between the two end effectors to perform a continuous, synchronized motion like wiping is immense.
Exactly. The left arm has to maintain the perfect amount of pressure on the plate to keep it stable, while the right arm applies this dynamic, sweeping force with the towel.
Yes.
And here, the robot just watches a human wash a plate once. It maps the task progress, hallucinates its own left gripper holding the plate and its right gripper holding the towel, and then executes the wiping motion, all adapted dynamically to its specific kinematic constraints in 29 seconds. It's just amazing.
It really is a marvel to watch.
Another great example from the paper is the flower sorting task.
Oh, the flower sorting task is great. It really highlights the fine-grained semantic understanding of the model. The robot is presented with a messy pile of red, pink, and yellow roses and tulips.
Just a total jumble.
Yeah. And it has to sort them into a vase strictly based on the sequence shown in the single human demonstration video.
Think about the layers of complexity there. First, the vision model has to accurately identify the specific flower species and color from a cluttered pile, which is a tough zero-shot vision task on its own.
Totally.
Then it has to align that semantic understanding with the human's intent from the video. And finally, it has to map all of that to a complex dual-arm trajectory to carefully pick up the thin, irregular stems and place them in the vase without crushing them with its rigid grippers.
It's so delicate.
The fact that it can extract that level of delicate semantic and physical detail from a single RGB video and execute it perfectly is mind-blowing.
It really raises a profound question about the future architecture of robot learning. By successfully decoupling skill acquisition from network retraining, Host proves that we don't necessarily need to keep retraining the quote-unquote brain of the robot for every new physical task.
Right, the knowledge is already in there.
Exactly. The latent representations inside modern large vision language models are already rich enough to bridge the embodiment gap. We just needed a better translation layer, like this self-grounded prediction cascade, to map the brain's existing knowledge into the robot's physical constraints.
So if you're building physical ML systems, the core takeaway from Host is this. You can solve the catastrophic forgetting problem by treating skill acquisition as a self-grounded prediction task aligned via smooth dynamic time warping.
That's the blueprint.
You get the immediate, lightweight adaptability of zero-shot execution with the high success rate of extensive fine-tuning, all while saving massive amounts of compute and data collection time. It is a huge step toward robots that can operate seamlessly in messy human environments, where anticipating every single edge case during pre-training is simply impossible.
It changes the economics of deployment entirely. You no longer need an entire team of engineers to teach a robot a new localized task. A single end user can do it with a smartphone camera.
Which leaves us with a fascinating and maybe slightly terrifying concept to mull over. If a framework like Host can successfully map a single human video to a completely different robotic embodiment in 29 seconds using these vision language action embeddings, how far are we from robots that can build an infinite repertoire of physical skills autonomously?
Probably not as far as we think.
Right. Just imagine a system scraping and watching standard YouTube DIY tutorials all day, learning plumbing, carpentry, and cooking, mapping those abstract human actions to its own motors, without a single line of task-specific code ever being written.
It's a wild thought.
We might be a lot closer than we think. That is it for our deep dive on AI Paper Slop. We will see you next time.